Hello there. Let's talk about UV spectroscopy. Where are quanta absorbed for UV spectra? Quanta absorbed are more energetic than X-rays and gamma rays, but less energetic than IR. Promotion of an electron from the ground state electronic level, let's call that S0, to a higher one, let's call that S1, requires a photon of UV light. Within each electronic energy level, there are multiple vibrational states. Electronic excitation most often proceeds from the most populated, lowest energy vibrational level. However, the electron can move to any IR state in the electronic level above it according to the quantum size. So a range of quanta are absorbed, and that is the reason why UV absorbances are broad. Once in the excited state, the electron rapidly sinks to the lowest vibrational level in S1, and then the energy is somehow dissipated after that. This series of lambda max values shows a steady red shift with more conjugation. Extending conjugation increases the length of the pi system, and that is called the cross-section. Degrees of absorbance are proportional to the compound's cross-section. Extending conjugation further eventually leads to compounds that absorb in the visible region. That is at the red end of the UV spectrum. Some of those compounds are responsible for vision in the eye, and others for natural colorings. For instance, beta-carotene gives carrots the orange color, and lycopenes, only one isomer is shown here, give tomatoes a red coloration. Everything we visibly sense is in the visible region. But how do we explain redshift of lambda max with extended conjugation? We need MO theory to do that. Ethene mixes two p orbitals to form its double bond. They contain one electron each, and both those electrons move down to the lower molecular orbital when the two p orbitals combine. In general, the number of atomic orbitals combined equals the number of molecular orbitals that are formed. Consequently, in 1,3-butadiene, the four p orbitals combine to form 2 pi and 2 pi star, and all four electrons move down into the bonding pi orbitals. Electrons promoted by UV absorbance correspond to the energy gap between the highest occupied molecular orbital, the HOMO, and the lowest unoccupied one, the LUMO. The same situation applies to 1,3,5-hexatriene. The 6 p orbitals combine to form 6 molecular orbitals, and the 6 electrons in those p orbitals move down into the bonding pi system. The reason lambda max shifts to the red on extended conjugation is that every time a double bond is added, the HOMO-LUMO gap decreases, and that corresponds to a smaller quanta, hence longer wavelength is absorbed. If you work in any laboratory related to the biosciences, including chemistry, you are likely to encounter UV methods to measure concentrations of compounds that contain chromophores. Chromophores are groups that absorb UV light. This is possible due to two observations. First, absorbance is proportional to concentration. That's Beer's law. Second, absorbance is proportional to the path length that the light travels through. That's Lambert's law. Together, these two laws form the Beer-Lambert law. A is absorbance, C is the concentration, L is the path length, and epsilon is a constant, the molar absorptivity for that compound under those conditions. Epsilon values facilitate comparing how effectively different compounds absorb UV light. All we need to know to measure the concentration of a compound in solution is Beer's law. A solution of the compound is weighed into a known volume of solvent, and then aliquots of that solution are stepwise diluted, retaining some each time. If Beer's law holds, a plot of absorbances of these solutions versus concentrations should give a straight line. If it does not, there may be precipitation or aggregation due to solubility issues, or the measurement range of the instrument may be saturated. Assuming the line is linear, if we then measure the absorbance of a solution of unknown concentration under the same conditions, this calibration curve, which in fact is a straight line, enables the concentration to be read. Determination of concentrations via UV is often more convenient and more accurate than any technique involving weighing. For instance, scientists often deal with samples of DNA that are too tiny to see. Happily, calibration curves have already been measured for DNA, so concentrations can be estimated by measuring the absorbance and then applying this equation. This estimate is far more accurate than weighing, and it's good enough for most situations. Similarly, for proteins, absorbance can be measured at 280 nanometers, then applying Beer-Lambert's law. A equals epsilon CL, where epsilon is taken from the literature according to how many tryptophans and tyrosines are in the protein. Trypt and ty are two genetically encoded amino acids that have significant absorbances at 280 nanometers. In conclusion, UV spectra are simple to record. Absorbances are broad because of the IR fine structure of each energy level. Conjugation increases the compound's absorptivity by increasing the cross-section and shifts lambda max to the red. These red shifts are due to the effects adding pi bonds to the conjugated system has on the molecular orbitals, and in particular, the HOMO-LUMO gap. Closer gaps correspond to lower energy, longer wavelength transitions. Finally, UV spectroscopy is a terrific technique for measuring concentrations of compounds, and this is particularly so for DNA and proteins. Thanks to everybody at the engine room, Southport, UK, for letting me use their wonderful studio. I hope this video contains quanta that correspond to your excitation states. Bye-bye.